Good afternoon. The proponents of the assigned group for Chapter 16 has chosen the topic resonance. In this lab experiment, our goal is to find the speed of sound at a given room temperature and the true value of frequency of the tuning forks. So let us begin.
The materials we will be using for this experiment are the following: a 1000 ml graduated cylinder, tuning forks of varying frequencies, which are 426.6 Hz, 440 Hz, and 512 Hz. A PVC pipe with measurement markings in increments of 10 millimeters, and a thermometer for measuring the temperature of the room. So first, fill the graduated cylinder with just enough water so that when you put the PVC pipe into it, the water will not overflow. Submerge the PVC pipe into the graduated cylinder with a 0 mm marking at the top, and get the room temperature to be used for future computation.
Then, get the 512 Hz frequency tuning fork and strike it with this stick. Then immediately place it at the top of the PVC pipe so that the sound produced by the tuning fork travels through inside the pipe. Slowly lift the pipe out of the water with the tuning fork. You should be able to hear a resonating sound within a certain length of the pipe. This resonating sound should seem to be louder than the rest of the sound.
The increase in volume happens when a standing wave is produced inside the tube. An antinode and a node is required. In this setup, the node is in the closed area of the tube and the antinode is in the open area of the tube. When you hear the increase in volume, the first antinode is at the open end of the tube that can only occur for a given wavelength at a certain length of the tube. Since this is a closed tube, only odd harmonics are possible. The first antinode that we hear is at a length of lambda over 4. The second antinode is at the length of 3 lambda over 4, and so on.
(200 millimeters). (190 millimeters). 170 millimeters. (200 millimeters). 185 millimeters. $165 millimeters.
In our experiment, we have found out that at room temperature of 27 degrees Celsius, the speed of sound is 347.2 meters per second. Using a frequency of 426.6 Hz, the speed of sound is 341.28 meters per second with a percentage error of 1.7%. In a 440 Hz frequency, the speed of sound recorded is 334.4 meters per second with a percentage error of 3.69%. A 512 Hz frequency produces sound that has a speed of 348.16 meters per second with a 0.28% error to the true value. In a room temperature of 25 degrees Celsius, the speed of sound is 346 meters per second. Using a frequency of 426.6 Hz, the speed of sound is 341.28 meters per second with a percentage error of 1.36%. A 440 Hz frequency produces sound that has a speed of 325.6 meters per second with a 5.9% error to the true value. Lastly, in a 512 Hz frequency, the speed of sound recorded is 337.92 meters per second with a percentage error of 2.34%. We also calculated the experimental value of the frequency of the tuning forks. In a room temperature of 27 degrees Celsius, the first frequency we recorded is 434 Hz with a 1.73% error. True value of frequency is 426.6 Hz. The second frequency, that has a true value of 440 Hz, we recorded 456.84 Hz, that has a 3.83% error. Lastly, we recorded 510.59 Hz from a true value of 512 Hz. It has 0.28% error. In a room temperature of 25 degrees Celsius, the experimental frequency that has a true value of 426.6 Hz is 432.5 Hz that has a 1.38% error. The second frequency we recorded is 467.57 Hz with a 6.27% error. True value of frequency is 440 Hz. Lastly, we recorded 524.24 Hz from a true value of 512 Hz. It has 2.39% error. In the data presented, we conclude that frequency and wavelength are inversely proportional to each other. As the frequency increases, the wavelength decreases. When the wavelength increases, the frequency decreases. For the speed of sound, it is directly proportional to both the frequency and the wavelength. Also, the factors that affect the experiment or the errors are the background noises, temperature that varies a little every second, and the surrounding air.